Hi, okay. So to finish off chapter 7, yay, we're going to talk about spin in the hydrogen atom, electrons. So what is spin and what is the history of spin? All right, well, we talked about in the last lecture how a charged particle moving in an orbit has an angular momentum. It creates a little current loop as it moves around the proton in the hydrogen atom, and then that current loop creates a little magnetic dipole moment for the atom. And in the presence of a magnetic field, this causes the splitting of spectral lines. It splits into odd numbers because of the values of the magnetic quantum number. There can never be an even number of possibilities for your magnetic quantum numbers because it runs from minus L to plus L, and L is an integer. So that gives you 2L plus 1 possible values for your magnetic quantum number for each value of L. So that's never going to be even. It'll always be an odd number. So this was understood and explained when Schrödinger solved the equation for the hydrogen atom, found the values of m sub L, and it explained the Zeeman effect, which was the splitting of spectral lines into an odd number. However, spectroscopists had also noticed splitting of spectral lines into even numbers of possibilities. For example, if a spectral line splits into 2, this is called a doublet. And spectroscopists had seen doublets, and they had also seen the splitting of spectral lines into other even numbers, such as 6. And so this couldn't really be explained by the Zeeman effect, what's known as the ordinary Zeeman effect, which we discussed in the last lecture. And it was strange. Now, in 1925, Pauly was studying some of these emission spectra with the weird results. Specifically, he was studying the emission spectra of the alkali metals. That's the first column in the periodic table. These have just one electron in their outermost or valence shells. And he introduced the idea of a two-valued quantum degree of freedom. Now, he didn't call it spin. And in fact, several physicists within the next year or so, including Kronig, Uhlenbeck, and Gutschmidt — I'm probably slaughtering the pronunciation of that name, and I apologize if that's the case. But anyway, these three different physicists all proposed the idea that you could explain this two-valued degree of freedom if you described the electron as a charged sphere that was rotating on its own axis. Now, after some calculations by some other physicists, it was shown that in order for this to happen, the electron would really have to be spinning at very high speeds, in fact, higher than the speed of light, and Pauly really hated this idea. So Wolfgang Pauli, who we'll discuss a little later in this course, he was the one that came up with the Pauli exclusion principle, if you've heard about that, and we'll talk about that later. Anyway, he was very influential in physics at the time. So him not liking this idea kind of shut it down for at least Kronig, who worked very closely with him. But Uhlenbeck and Gutschmidt, they worked for another guy named Ehrenfest, and Ehrenfest encouraged them to publish this idea. And so they did, and this idea was published. This is a picture of Uhlenbeck and Gutschmidt in 1926, right around the time that they published their idea of electron spin. Now you might be thinking, what do you mean electron spin, and how would this explain anything? Okay, well, this is something that's often covered in intermediate physics 2, okay? So if you have a charged ball, and I'm not talking about electrons specifically here, but any charged ball, like a macroscopic one, for example. So you have a uniform ball of charge, and then you set it spinning on its own axis. Now, if you take a top-down view of that, which I've depicted in this little cartoon here, in this case, X is the rotation axis, and the direction of rotation is shown there. Now, if you look at just a little slice, which I've indicated here in purple, of this charged sphere, then what's happening is there's charge in that sphere that's rotating. And so basically, that slice is making a little current loop. And of course, we know that current loops create magnetic dipole moments. We talked about that in the last lecture. And so if you have a charged body that's rotating on an axis, it's going to have a magnetic dipole moment, just like an electron, for example, moving around creates a current loop. It's the kind of same idea. And so this was the idea that was proposed by several physicists during this time. If you had an electron, it was a charged ball, and it was spinning around on its own axis, then you could get a magnetic dipole moment out of that, and it would have these 2 degrees of freedom, and that would explain the results that they saw in the emission spectra for the alkali metals. Now, the idea of the electron spin kind of stuck because it solved so many problems. It didn't just solve this idea of what they saw in the spectra, but it also explained the results of a very influential experiment called the Stern-Gerlach experiment. The series of these experiments was conducted in 1921 and 1922. So despite Pauli's objections, this idea of electron spin kind of persisted. And then in 1928, Dirac, shown here in this image, his name is Paul Dirac, he developed a relativistic quantum theory, and that explained away Pauli's objections. And the electron spin as we know it fell out of his equations. And so that was nice, and Pauli lifted all his objections. All right, so what was the Stern-Gerlach experiment that I talked about? Well, what they did was they had 2 magnets set up, creating a non-uniform magnetic field in the direction that they called the Z direction, and they passed a beam of silver atoms through this non-uniform magnetic field. Now, the field had to be non-uniform. It couldn't be a uniform magnetic field, or there would have been no net force. And you can see this if you use the idea, and this is very straightforward physics right here, physics 1150s type stuff. The force is defined as the derivative of the potential energy. So if you take the force in the Z direction on those silver atoms going in there, the potential energy that you would plug in would be that mu dot B potential energy that we discussed in the last lecture, okay? So what you're doing is you're taking the derivative with respect to Z of mu dot B, which gives you mu ZB. Okay, so if you plug that mu ZB into that equation, the mu Z would be a constant that would be the same for all the electrons and for the particles. So you pull that out front, and then you're just left with the derivative of the magnetic field with respect to Z. Now, if B is a constant, if it's a uniform field, then that derivative goes to 0 and you've got no force. But since the magnetic field strength changed between the 2 magnets, then that gave them a field gradient, and so they saw this net force. Now the force would be also proportional, though, to that magnetic dipole moment, okay? And so what they saw was because electrons had this inherent net magnetic dipole moment with 2 possible values to it, they saw a splitting of the beam as it passed through into 2 distinct beams, okay? And that's pictured here on the right. This is the results of the Stern-Gerlach experiment. They set up some photographic paper, and then they passed the silver atoms through, and then the top image is what they saw when there was no magnetic field, when the field was turned off. And then the bottom image clearly shows the splitting of the beam into the 2 possible values when the magnetic field was turned on, okay? All right, so here's a little schematic of the Stern-Gerlach experiment. They had their silver atoms, which they put in an oven, ejected them out into a beam, and then it passed through this non-uniform magnetic field, and then the photographic plate was on the other side, and it got exposed when the atoms hit it, okay? And then they saw that splitting into 2, okay? So this helped explain some of the results that they got from spectroscopy, because if you've got 2 possible values for your electron spin, right, then that gives rise to even numbers of splitting in the spectra, okay? Now, the concept of a spinning electron, if an electron sitting there and spinning on its own axis, that's conceptually quite useful. But experimentally, as far as we can tell right now, electrons are point particles without any spatial extent. So I'm not sure how something that's got no diameter can spin on its own axis. I don't know. So the experimental evidence just supports the idea that this magnetic moment, this inherent angular momentum and this inherent magnetic moment, for those 2 concepts go hand in hand, it's just an intrinsic particle, a property of that particle, all right? So particles can have an intrinsic, inherent angular momentum and magnetic moment, just like they have a mass or a charge or any other property. So it's just one to add to the list. And this property, this inherent magnetic moment, is called spin. All right, and we're going to use a new quantum number, actually two new quantum numbers to describe it, S and m sub s. Okay, so it's important to remember that this electron spin did not fall out of the Schrödinger equation. The Schrödinger equation gave us three quantum numbers, and now we have four, okay? The three quantum numbers describe the 3 degrees of freedom. This fourth quantum number is used to explain experimental results. However, later it was derived from Dirac's relativistic quantum equation, which we will not cover. It's pretty hard. Okay. Okay, so if you picture it, we'll call the angular momentum resulting from the inherent spin of the electron. We'll use S for that, okay? S for spin. And it's got two possible orientations in the presence of a magnetic field, an external magnetic field. It can either be spin up or spin down. Now remember, just like the other angular momentum, your angular momentum cannot totally align with the field. This is due to the uncertainty principle. So it's going to sit in an angle to the field and precess around that external magnetic field, forming that cone. And it'll do that either mostly aligned with the field on average or anti-parallel to the field on average. And that's your spin up and your spin down states. Okay, so now you've got two forms of angular momentum. You've got your orbital angular momentum, L, and you've got your spin angular momentum, S. Okay? The quantum number that we'll use to put in terms of the total angular momentum will be lowercase s, and S is always equal to 1/2 for an electron, regardless of the electron, regardless of where you put it, in what atom, in what energy level, little s is always equal to 1/2. It never changes. So the magnitude of the spin angular momentum, we're going to use the same form that we used for the total angular momentum in the orbit, okay? Remember that the magnitude of big L was equal to the square root of little curly L times L plus 1 times h bar. And so the form for the magnitude of the spin angular momentum is the same form, but it's the square root of little s times s plus 1 times h bar. And this gives it a total magnitude that is constant for every electron, and it's √3/2 h bar. All right. Now the magnetic spin quantum number, little m sub s, that's where your differences fall. Little m sub s can range from -s to +s in integer steps, but because s is always 1/2, that always puts m sub s as -1/2 or +1/2, and that's it. Okay. So it's two possible values. +1/2 is the spin up case, and -1/2 is the spin down case. And of course, the z component of the spin angular momentum is m sub s times h bar. This is equivalent to the Lz is equal to m sub l times h bar. Okay, same kind of idea. And that puts the magnitude of the z component of the spin angular momentum as plus or minus h bar over 2, depending on whether or not the spin is up or down. Okay, so spin angular momentum is quantized, just like orbital angular momentum is quantized. This is quantum, everything is quantized, okay? Hence the name. Okay, now, the magnetic moment due to the spin is related to the spin angular momentum, of course. The magnetic moment magnitude is equal to minus e over m times the spin angular momentum. And then the z component of the spin magnetic moment can have values of plus or minus eh bar over 2 times the mass. We now know that spin is an intrinsic property of particles, just like charge or mass or whatever else. We also now know that protons, neutrons, and electrons, in fact, all the ordinary matter that we deal with on a day-to-day basis is made up of spin 1/2 particles, okay? So since protons, neutrons, and electrons make up ordinary matter, all right, they make up all the atoms that we deal with on a day-to-day basis, ordinary matter is all made up of what are called fermions. Fermions are a class of particles that are spin 1/2 particles. There are particles that are integer spin. Those are usually exchange particles. Don't worry, we'll talk about it later. Anyway, integer spin particles are called bosons. Bosons can be photons. We'll talk more about that in a second. And then other particles that are carriers of force, like the Higgs boson. You might have heard of that one. And there's also composite particles. So if you cram a lot of fermions together, like say in an atomic nucleus or something like that, let's say, for example, you have a helium nucleus with 2 protons and 2 neutrons, then that can sum to an integer spin. That makes sense, right? And then those can be what are called composite bosons. Okay, moving on to a slightly different topic, but still dealing with the idea of spin in a way. Let's talk about selection rules. Okay, so if you look at a hydrogen atom spectrum, what's happening is the electron in the hydrogen atom is making transitions between energy levels, all right? And then when it makes those transitions between energy levels, for energy conservation, for example, if it's an emission spectrum, it'll emit a photon. And that's when the electron at a higher energy level decays into a lower energy level, and then for energy conservation emits a photon, all right? Now, it turns out that there are rules about what transitions the electron can make, right? The other transitions are called forbidden transitions, and those the electron is not allowed to make most of the time, okay? It'll still occasionally make a forbidden transition, but the probabilities of forbidden transitions are really, really low. They don't happen often. You might be thinking to yourself, please tell me what these selection rules are. Well, here they are. The electron can only transition between energy levels when it changes the value of the orbital quantum number L by plus or minus 1, okay? So it can go from an L equal 2 to L equal 1 state, for example, but it can't go from an L equal to 1 to L equal to 1 state. That's forbidden because delta L doesn't equal plus or minus 1 there. So that's the way it goes. Now, also, the magnetic quantum number can only be allowed to change by either nothing, 0, or plus or minus 1. Larger steps than that are not allowed. So for example, you couldn't make a transition from an ML equal to 3 state to an ML equal to 1 state. That would be a forbidden transition. Why? Okay? First they noticed that this was the way it was, but then they started asking themselves why this was the case, pretty much immediately, because after all, they're physicists. Well, it turns out that in addition to conservation of energy, another thing that we physicists have a tendency to hold sacrosanct is conservation of angular momentum, all right? So the angular momentum of the entire system, atom plus photon, that has to be conserved, right? So these forbidden transitions are ones that violate conservation of angular momentum. And that's why they don't happen very often. There are some weird cases when the angular momentum can be conserved in other ways rather than just the photon. And that's when the forbidden transitions happen for the most part. But most of the time that doesn't happen, and so the transition is forbidden. Now, what does this mean for you? Well, it means, and I know this is strange, a photon has angular momentum, okay? Photons have angular momentum. I know a lot of people had a lot of trouble with the idea that a photon had momentum in the first place. And so it's going to be pretty mind-boggling to deal with the idea that a photon has angular momentum too, but it does. In fact, the photon has angular momentum equivalent to that of a particle with spin 1. So photons have spin, which means photons have intrinsic angular momentum. That means photons have energy, linear momentum, and angular momentum, all three. Now, if you think about it, this kind of makes sense, all right? We've discussed how magnetic moments and angular momentum are related. So if you can get around your head around the idea that a photon has to have a magnetic moment, then maybe you can get your head around the idea that it's got an angular momentum, right? Okay, well, why would it have a magnetic moment? Well, if you think about the magnetic moment as sort of an average magnetic field created by a particle or the orbit of a particle, and you think about the fact that light is an electromagnetic wave, right? Light is a self-propagating, oscillating electromagnetic wave, right? So what that means is it's got an electric field and it's got a magnetic field, and they're bobbing back and forth, okay? So it's an oscillating magnetic field there. Well, that means that it's got some kind of average value of the magnetic field. This average value of the magnetic field, the direction that this average value of the magnetic field points in, this is related to the polarization of light. You, of course, probably have heard of polarization through Polaroids, polarizers, and all kinds of things like that. So light can be polarized. That means that light has an inherent magnetic moment, okay? And that means it's got angular momentum. So there you have it. Kind of makes sense. It turns out, like we said, light is a boson. It's a spin 1 particle. If you go on and study this more in upper levels, you'll learn that the spin 1 comes from circular polarized light, okay? So if you have circularly polarized light waves, that means that the magnetic field does this. It's kind of rotating around the axis. Now, you can either be rotating like clockwise or counterclockwise, and those are the two states that dictate the spin of the photon. All other spin, like a vertical or horizontal spin, all other polarizations, like a vertical or horizontal polarization, you can think of that as a subset of a circularly polarized wave, right? Okay, so if you do that, then you can imagine that you've got this inherent angular momentum due to it either being a left or right circularly polarized light. It turns out that when a light beam is circularly polarized, each photon of that light carries a spin angular momentum of plus or minus h bar, okay? The left one is the plus, the right one is the minus. Okay, so photons have angular momentum. Hopefully that's mind-blowing enough for today. And that finishes off Chapter 7. Yay! So you're now ready to do the Chapter 7 homework. Boo! Anyway, so see you in the next lecture, and if you have any questions, let me know.